chemistry. Last time we looked at benzene. This time I want to have a look at more about the Friedel-Craft's reaction and halogenation, moving on to phenol, and we'll see how we go from there. Right, let's have a look and get started. If we take my benzene ring, then we remember from last time this is delocalized. So what we've got is, instead of having the electrons basically in sort of above each atom, they're spread out all around, and this gives rise to all sorts of problems and properties that we have to deal with. We can look at the benzene as this type of ring instead, where we can sort of try and cope with it in a slightly different way. Right, so these bonds are just bigger so we can see what's going on. Now if we have a look at what's going on, let's cast our minds back to having a look at perhaps a simpler chemical. And the one I want to have a look at is ethene. Right, so let's just look at a simpler molecule so we understand how this might be working, and then we'll move on to understand how the benzene is going to react. So I've got here a double bond, and this we can think of as just one part of this benzene ring. Now if I want to do some sort of halogenation of this, then we bring in a molecule like bromine. Let's draw out what we see here. So I've got my ethene, and I'm bringing near to this, let's suppose I'm going to bring in some bromine. So what's actually going to happen? Well, this double bond here is rich in electrons. Bonds are made up from electrons. So this tends to be a more negative center here. The bromine is a dipole. It sort of makes sort of these instantaneous dipoles. One moment this might be slightly more positive, this might be slightly more negative, then this might be slightly more negative, this one might be slightly more positive. And so let's imagine that this one here is very slightly more positive and the other one slightly more negative. These are sort of instantaneous dipoles. This means that this bond is negative, this is positive, these are attracted to the bromine. So the electrons leave here going to the bromine. So I can sort of represent that here, I suppose, by breaking my bond. Goodness me. And as I break this bond, it isn't going to fit nicely. It's attracting to this bromine. As it does so, this bond passes its electrons to that bromine, and this bond is broken. So we've got a bond broken here, and I'm going to pull it off and desperately try to remake the bond here. So if we look at what's gone on, we've now got a situation where I've got this bromine attached here, but this carbon has the wrong valency. This one has got a spare, if you like, set of electrons. Just reaching offset for my extra little bits. So this bond, I'm going to have to break the bits you're missing, and me trying to pull those bits apart as hard as I can. And there we are, managed to push the two together. So we've now got this here. This is a carbocation, and that is fairly close to a Br minus, and the Br minus here is going to go in to this carbocation, and as it does so, it forms a bond with the ethene, giving us here bromoethane. And this is standard electrophilic substitution. Can we imagine the same sort of thing working with the benzene? So I've got here my benzene with its 6 carbons, 6 hydrogens, and we can think of each of these bonds as being really equivalent to 1.5. Definitely more than 1, but less than the double bond. If I bring in something like bromine here, then it's not really going to stand half a chance getting in there. Yes, we can make this an instantaneous dipole, make it slightly positive, but this ring here is remarkably negative, and it's remarkably stable, so it's not going to want to do anything. So we need something a little bit more powerful to try and get this bromine to react. Instead of making it delta positive, I'm going to have to make it proper positive. So some pioneering work was done in Paris in the 19th century by 2 chemists, and they were a guy called Charles Friedel and another gentleman, an American called James Crafts. And this is done during the 19th century, and they developed a technique whereby they made this bromine more positive. And after a lot of work, they started off with iron chloride. Doesn't matter if it's iron bromide, whatever, we're going to start here with the chloride. Basically, we've got to try and break this carbon-hydrogen bond, but it's linked into here. So we've got to try and work on this to sort of make it break. So we're going to pretend this is chlorine this time, and we're going to meet iron chloride. Now the general mechanism for this can be really that we can take any particular chloride where R is going to be some sort of group. So we could take this particular compound. I have my molecule a little bit bereft of hydrogens there. So I've got this chemical here. Okay, so it's just a chemical, and what we're going to do is we're going to bring this fairly close to the other one. Now what's going to happen is this chlorine, which is fairly negative, is going to react with the iron chloride, and that is going to form this. This is now FeCl4, and this is remarkably minus. So let's see what we've got. We've got our benzene ring. And what I want to do to this is I want to attach this R group. It's reacted with the FeCl3, so I've taken my chemical, which is here RCl. I've reacted this with my FeCl3, and this has given me this R plus chemical plus FeCl4. Now FeCl4 is quite negative. This is quite positive. So when they are all in close proximity with one another, what we're going to get is this happening. Our intermediate is going to form. Let's draw that out. And as we did before, we've got to draw in our delocalized electrons being broken. I'm going to make sure I'm below that line. And here's my delocalized electrons. We're showing this is now positive, and my H, we've also got the R group attached to that. Hanging around in the winds is this FeCl4, and the basic idea of this FeCl4 is this Cl on the Fe is going to come very close. I haven't drawn those in because it's just in the way of everything else, and this is then going to form HCl, plus we're going to get our substitution done. The ring's going to be made up, the hydrogen's left, and now we've got our R group attached to our benzene. With the elimination of HCl, the Fe4Cl makes Fe3Cl, so we've regenerated our catalyst. So let's look at this. We've got my benzene, we've got this close proximity, this is going to react with my hydrogen, making my HCl. This is going to be regenerated. I'll put my lone pair back, and this is going to be stuck on to my benzene, and I've now made a new chemical. So this way Friedel and Crafts managed to work out that they could stick on more or less any group they wanted to a benzene ring, and that proves to be quite useful. So we can do more or less anything we like with this. But they found there was a better way of trying to do this. In this mechanism, we've got to have our group come in with our FeCl4. If we made this more powerful, we could do something about that. And with a bit of luck, there we go, I can come along with a new chemical. So I'll just chuck some more on the floor. So here we've got made an acyl chloride. It's got a double bond O and a Cl, and this can be anything we want. So this is now really quite powerful, and using the Friedel-Craft reaction we can take our benzene, so let's just zoom in a bit, and this time it can meet this substance which we've got as an acyl chloride. It's 2 carbons here, so ethanol chloride. And that is going to react with our benzene. When we do this, this reaction is called acylation, and what we want to do is to basically cook this at about 60 degrees Celsius for about 30 minutes. We need to try and help this along though a catalyst, and along comes our favourite Friedel-Craft's catalyst. This time it could be something like aluminium chloride, and we get a reaction. Now this has got to be anhydrous. Why? Largely because we've got this nasty crisser around, and this isn't going to do much good if we've got anything like water around. And what's going to happen? The same things are going to happen. So this is going to react with the aluminium chloride, and the reason I'm swapping these over is simply I can't get the bond out. So we've made our aluminium tetrachloride. This brings this right next to here as our intermediate. We're going to get our reaction with our chlorine. So I'm going to produce my hydrogen chloride, and we're this time going to manage to attach a more powerful group to our benzene ring. And so this time we've got something a little bit more powerful added. Let's draw that out. So I've got this going. We're going to get here our intermediate. I'm going to draw in the loop with my plus sign. I've got my H here, and this time we've got attached to this the group here. So we've got my C and my CH3, and we've got my double bond O group there. This is going to react with this time the aluminium chloride. Just got about room to put this in here, and that's going to give us HCl. Is going to regenerate our aluminium chloride catalyst, and we're going to get our benzene ring reformed. We've lost this H with that Cl to make HCl, so on here we've got this, and whatever group we really wanted to put on here, and this could be any particular group, and we've managed to make more or less any chemical shoved onto a benzene ring. It's quite useful. Friedel-Craft's worked quite hard on trying to do this. So the acyl chloride basically gives us more power to do things than otherwise. Its functional group, the C double bond O, is, there we are, pulled it apart, much more reactive, and this little thing gives us a lot more power to actually choose what we want to do. We could just, rather than substitute with one thing, we can put a whole load of groups on here, and as long as we've got something, we're all right. So why only one reaction? Well, when I'm shoving this on to this benzene ring, we're basically making a ketone. If we look at the structure of this, we've got any group with a C double bond O in the middle. It's a ketone. Ketones aren't terribly reactive, so therefore only one substitution takes place. Let's move on from benzene and look at something which is a little bit more lethal, and we'll have a look at phenol. Going over here, we're going to just try and change this to phenol. I was having problems trying to pull it apart. Let's make our phenol. So what we're going to do is we're going to put on here our OH, so that we can create our phenol. There's my full stick model of the phenol. If we want a more compact version of the phenol, then we can look at that. Like this. So benzene with an oxygen and a hydrogen attached to it. This should be an alcohol, but it certainly isn't, and instead this is a phenol group ready to react. So let's look at what we can do with this phenol. Now, with this phenol, what I'm going to try and do is attach some other bits and pieces to it and see what we get. I'll move this one out of the way and we'll look at this bigger stick model. So all we've got is an hydroxyl group attached to this aromatic ring. Now, if the hydroxyl group is attached to an alcohol chain, then it's no longer a phenol derivative, and we describe that as an aromatic alcohol. So if I have, for instance, this subject, then although it's got the same basic structure, here this is not thought of as a phenol, but this here is an aromatic alcohol. So this would be called phenyl ethanol, but it's not a phenol. Whereas if we take this one this way and we start off with the phenol, and to this I attach the ethyl group, got it round the right way. Here we've got, starting at position 1, 2 ethyl phenol, and this is a phenol. Phenol is a weak acid. It therefore means it partially dissociates in water, and we could have a look at that. I suppose we ought to write that one down. It's a thing that we need to sort of be aware of. So if we have our C6H5OH and we add this to some water, which is necessary to make an acid, then we get our C6H5O-, and we get H3O+. And of course this can go both ways. If I react my phenol with something like sodium hydroxide, then what we're going to get is my salt, C6H5O Na, so this is going to be O minus Na plus, and again plus water. So we can make quite interesting sort of bits and pieces. So this is sodium phenoxide. Right, our reactivity of our phenol is significantly different than the benzene. So if we take this and we bring near this some bromine, then what's going to happen, it's going to substitute at positions 2, not 3, 4, that's it, and 6. I should have done that further away, then you could have seen it a bit better. You could have seen me struggle trying to get these things apart. So our reactivity, we find that phenol is more reactive than benzene. This is due to this extra lot of electrons that are pulled out towards the oxygen, making this ring slightly more reactive. So these p orbital electrons from the oxygen are added to this delocalized structure, and it makes it more nucleophilic. The increase in electron density then allows it much more susceptible to electrophilic attack with something like our chlorine, bromine or whatever coming in. Because as a nucleophile here, this is going to do much more to induce a dipole if this is something like chlorine, bromine coming in. So if we look at that reaction by phenol, and we can add to this some bromine, and we probably about 3 of those, that's going to give rise to two, 4, 6 tribromo phenol. If we want to do electrophilic substitution here with our phenol, then we can have quite a lot more fun. And if I get some extra bits here, I'll throw one over there. Right, let's see what would happen here. I'm just making up something to play with. Right, let's get our phenol back, These things I find are either too loose or too tight. Never, alright, that one was quite as I want them. Okay, so let's look at something like nitration. We've looked at bromination, now let's look at nitration. Phenol will undergo this single step substitution reaction with dilute nitric acid, and this is going to be at room temperature. So let's just take this, and it's going to form basically a mixture of either it's going to go in at the 2 position here, and this is going to give us 2 nitrophenol, or it will quite happily go in at position 4 no, didn't, still not going in, there we are, or it's going to give us 1, 2, 3, 4 nitrophenol. So 2 nitrophenol or 4 nitrophenol. If you want to have much more fun with this reaction, instead of using dilute nitric acid, you can use conc nitric acid. Then what we'll get is a triple substitution, and we'll get in here, just making the molecule there, just so you can see it. We've got here 2, 4, 6 trinitrophenol. Trinitrophenol, a really nice, friendly, safe substance to play with, as long as you don't value your fingers that much. Let's look at the position of this substitution and see what happens. So let's take these nitro groups off. We'll go back to my basic benzene, and let's bring in a different group to react, and we'll bring in here an NH2 group. So we're going to bring in here an NH2 group, and we're going to replace my phenol here with an NH2. So we've got here what substance? So this is a phenylamine. Now this phenylamine is going to react with bromine. The nitrogen's going to work exactly the same way as it did when we had this oxygen. Let's just take that out of the way so it's a bit clearer. What's going to happen is this nitrogen again is slightly more electron dense, and so these p electrons are going to join in with these delocalized electrons, making this again more nucleophilic. So in exactly the same way, then we can bring in our bromine, and our bromine will either go in the 2, the 4 or the 6 position. In fact, it's so reactive here, it's going to go to all of them. Now this is known as the directing effect, and it happens when we've got things like this nitrogen here. Now when we swap this amine group with an NO2 group, this is slightly different. The nitro group, because we've also got these extra oxygens, is going to bring out, instead of adding to this, it's going to bring these electrons out. And what this does is, when you react this with bromine, chlorine or similar, it's going to have a 3 directing effect. So we're going to get our bromines, rather than substituted at 2, 6 and 4, we're going to get them favoured coming at this position. So when you want to try and build something with benzene and its derivatives, if you want to place things at different positions on this benzene ring, then you've got to be aware of what sort of groups you've got on. If you want a 3 directing effect, then you need a substance like NO2 up here, which will withdraw electrons from the benzene ring, pointing to a 3 directing effect. Or if you want to have a 2, 4, 6 directing effect, then you can put on a group such as a phenol group or an amine group, and that will direct this substitution to 2, 4 and 6. Controlling, if you only want one bit of substitution, we tend to use weak substances, and if you want multiples, then you tend to use strong substances. So there's an idea about benzene and a few of its derivatives to give you some idea of what they do. There's a whole series of different sort of problems and questions that we can come and have a look at with this, but basically this is the important things that we actually do. We can make some other interesting ones. Let's just quickly have a look at some of these. So if we go back to my phenol, we can put on some rather interesting other chemicals. So let's see if we can do one of these, and I'm just going to take my carbon atom, go the right way. Right, so let's have my carbon atom. Let's make here a carboxylic acid. You're missing the exciting bit of me trying to pull the things apart. So with our carboxylic acid, if we can attach this, there we go. Then we're going to get something like not strong enough, there we are, a phenol with a carboxylic acid on. Now this one causes my students usually a lot of problems trying to name this. This is benzoic acid, and if I put on here, this is going to be, looking it round this way, 2-hydroxy benzoic acid. If I've replaced this with my NO2 group, then this is going to be 2-nitrophenol. And if I put some more carbons in there, we remember this is going to give me something which is slightly different. So that might give me something like 2-phenyl ethanol. So some interesting sort of features of trying to do some of these reactions. Directing groups, then we think of either the NH2 or the OH as a directing group for 2, 4 and 6, and we think of the other group here, the nitrobenzene, as a 3 directing group. In the old days, which is before my time, then we used to think about these with different names. And I'll just take this group here, and we used to think of something as at position 2, we used to call this ortho. So we might have this, rather than 2 something, this would be ortho something. Position 3 becomes meta, and position 4 is para. So if I look at my nitrobenzene here, if I take my nitrobenzene and we shove something on here, for instance, let's shove on something like a methyl group. If I was shoving the methyl group on, then this would be something like para nitro. Well, this is going to be toluene, but yeah. So let's do a different one. So I could have NO2, and if I put the Br here, he says not being able to stick anything on. So if we have this one here, then this would be something like 2-bromo nitrobenzene, or it could be called position 2 ortho. Remember, if we actually had that there and we were substituting the bromine on, it would go to this group by preference, and this would be meta bromo nitrobenzene. So the 2,4 directing groups, the ortho and para directors, are basically things like phenol and the amine, and the nitro group tends to be ortho or 3 directing. Telling you the same thing but slightly different ways. Let's predict what might happen. So let's start off with methylbenzene. I know this is toluene, and let's look at what we can do with this. This CH3 group is 2,4 directing. So if I'm going to substitute bromine, then it's going to come in either at position 2 or position 6 here, or position 4. If I make this and it only substitutes one group in here, so we've got perhaps one bromine coming in here, then I'm going to get this chemical, and of course I'm going to get its sister, this chemical, which are exactly the same, and I'm also going to get this one down here. So how much of these am I going to get? If I make this stuff, which is, this is toluene or methylbenzene, so this is going to be 4-bromo-methylbenzene, or we can have 2-bromo-methylbenzene. We'll find we end up with twice as much 2-bromo-methylbenzene as we do with the 4-bromo-methylbenzene, because there's just going to be this one and this one formed as much as that one, so we're going to have 3 lots. 2 of them we were going to regard as the same and the other one is different, so we're going to have a 2-to-1 mixture of the chemical as it's made. So when you need to try and plan an organic synthesis, which is usually part of the big fun of trying to make bits and pieces like this, you have to think about what I'm trying to do, and what you're trying to do is, do I need something to be 2,4 directing, or do I need something to be 3 directing? And if you need that, you have to sometimes think that it may not be better to start with adding this group, but it might be better to add that group, because if you add this group it might go in the 3 position, whereas if you add it the other way round it might go to the 2, 4, 6 positions. So you have to do a little bit more thinking when you come to doing organic synthesis. So hopefully that's given you a better idea of these nasty critters, these arenes. I hope that's been useful, and I hope to see you next time, and we'll have a look at some more nasty critters. My suggestions I get from the feedback is that organic chemistry is your pet hate and the bit you find more difficult, so we'll push on and do a little bit more with this. So if you like what you saw, you can always subscribe, and I'll see you same time next week. Until then, bye bye.